Hello, everybody. This is our last talk today for the summit. I hope after this, you'll go back to the main room for Ship It Live. Highly encourage you to check out Ship It Live. It's one of my favorite parts of Summit. My name is Luke Kilpatrick. I've been your MC for this track. And we have Nathan with us to talk about Connect, AWS, and Docker with Bitbucket Pipelines.
Thanks, man. So a little over a year ago now, a small team of designers, developers, and product managers from the Bamboo team in Sydney were given the opportunity to build a new continuous integration tool for the cloud. One of the goals for the product was for us to democratize continuous integration and delivery by bringing it to all users of Bitbucket Cloud. And we built the beta of this in 9 months, which we unveiled at Atlas Camp last April, and we made generally available to all users of Bitbucket yesterday. Hi, I'm Nathan Burrell. Whoops, wrong note. Today, I want to cover 3 areas that helped us achieve these goals by using pipelines as an example as to how you could build an integration like this. First, I want to talk about Connect. Connect is a platform to allow you to build seamless integrations with all of Atlassian's cloud products. Then, I want to talk about how we run our microservices and interact with AWS. And finally, how we use Docker to speed up our local development, and also how we run it securely in the cloud. So Connect is a platform to allow you to build integrations with Atlassian's cloud products. It consists of three sections. We have a Connect descriptor that describes how to wire up your integration. You have iframes and webhooks, which are 2 powerful integration points that Connect exposes to allow you to inject UI fragments and receive notifications of events, and uses JSON Web Tokens for security. So let's start with the Connect descriptor. This is the first piece of Connect that you usually interact with as a developer. This little piece of JSON, which you host alongside your application, describes how your integration is wired up with the Atlassian, with the parent product that you install the integration to. So here we have the scope section for Bitbucket Pipelines. These permissions are associated with all requests that you make, either via the iframe bridge or from your microservices back to Bitbucket, and they're associated with the JSON Web Tokens that you generate. Here, there are 3 levels of these scopes. So for pipelines, we need account read, repository admin, and we have read access to pipelines and their associated variables, so our UI can actually render these. So after you set from the scopes, you then probably want to start injecting UI into the Atlassian product. Here we have how to configure iframes using the modules web panel section. This is an example of the pipelines overview page, which is displayed when the user selects the pipelines icon in Bitbucket's side panel. It has a location, as there are multiple iframes in Bitbucket that you can actually inject UI into. And we have a URL. Whenever a page is loaded, Bitbucket will then make a request to this URL for the content. It also has some additional query parameters here. The Bitbucket, when it makes the request, will expand to give you contextual information as to the surrounding page, so you can show relevant data. And you can also set conditions on these to show or hide them, depending on whether a user is a part of a specific role, or you're dark featuring it, or there's a certain file in the repository. The final part of the Connect descriptor are webhooks. Webhooks allow you to receive HTTP requests when certain events occur in the Atlassian parent product, such as a user pushing code to a repository. In this example here, you can see that it has a URL. Whenever a user pushes code, this URL is called. A HTTP request is made to this URL, which one of our microservices then actions. I've also highlighted the lifecycle section. While these aren't webhooks per se, they behave in much the same manner and usually called when certain events occur with your integration, such as when a user installs it or uninstalls it. The user then, on an installation, will also have to accept the permissions that you set in your scope to allow your integration to make those requests. The installation one is also of particular importance, as this is where the handshake occurs that gives you a shared secret that you can use to generate JSON Web Tokens. So now that we've seen how with a few small lines of JSON, we can specify the entire configuration of the integration, let's dig a little deeper into the 2 main integration points that Connect provides to you as a developer, which are iframes and webhooks. Here we have an example of a build result page for pipelines. Everything that is highlighted is actually an iframe that is not part of core Bitbucket. It's actually served up from one of the pipeline's microservices. What happens is when this page is rendered, is Bitbucket will inject some JavaScript into your page, a library called AP, short for Atlassian plugin. What happens with this is it allows you to have a 2-way communication bridge between your iframe and the parent application. You can then this can then be used to interact with the parent product. You can use this to show modal dialogues or to make further requests for more information. How this actually works is that JavaScript has an event bus built in called postMessage. Whenever your iframe makes a request for data or wants to show a modal dialog, it'll place a message on this bus that the parent product then listens for and actions. Now let's talk about some webhooks. Here we have Bitbucket and a microservice from Pipelines. Whenever a user pushes code to Bitbucket, we receive a repo push request. The body of this request contains the committer, some of the commits that were done, and any references that were modified, such as tags and branches. What Pipelines then does is it actions this, and this is how we trigger off the build processes. We make subsequent requests to downstream services to actually perform it, and then they launch events to process your pipeline. So we've seen with iframes and webhooks, you have two powerful integration points. But how are these secured? Obviously, everything is over HTTP, and how can you be sure that the calls are coming from Bitbucket? Bitbucket Connect uses a technology called JSON Web Tokens. JSON Web Tokens are a user-friendly and compact way to provide authentication information with requests. They consist of three sections. You have a header, which tells you the algorithm that was used to generate the request, to generate the token. You then have a claims section that designates the user that created the JWT token, contextual information about what's requesting, and a URL. You then take these two sections of JSON, you can concatenate them, you base64 encode it, and use the hashing algorithm that you specified in the header and the shared secret that was shared during the installation flow to generate a token. When you make a request to Bitbucket, we then attach this as a header parameter. Bitbucket then knows that we're trying to authenticate with JWT, and it will use in the shared secret that only Bitbucket and Pipelines knows, or your own integration, to code this JWT token and choose whether to action the request or not, based on this being valid. So what happens when Bitbucket actually makes requests back to your integration, such as Pipelines, for more data? Well, Bitbucket also attaches to all request JWT tokens. It's then up to you as an integration developer, or us as Pipelines, to decode this token to make sure that it's valid, and then we action the request if it's found that it is. However, not all endpoints in Bitbucket actually can be authenticated with JWT, with JSON Web Tokens. Cloning over HTTPS is one such request, and this is quite important to Pipelines. But what Bitbucket provides is an access token endpoint under the OAuth site path in Bitbucket. You can then make a request to this and attach a JWT token to it. What will happen is Bitbucket will decode this JWT token and return you a response, the body of which will contain an OAuth token of equal scope to the JSON Web Token, and then you can perform, say, a clone over HTTPS, which is how we perform clones in Pipelines. This is quite nice, as it saves us from having to set up complicated SSH keys or add a specific user to every single repository to be able to clone the code. So that we've seen with Connect, you can build transparent integrations. And with iframes and webhooks, you provided two powerful integration points, and you can secure it tightly using JSON Web Tokens. So you've probably heard me mention a few times now that Pipelines uses microservices. So what do these actually look like? What are the libraries that we use to build them, and how do we run these on AWS? Let's go over the typical anatomy of microservicing pipelines. I'll talk about some of the libraries that we use, and how we interact with downstream services. Here we have a typical microservicing pipelines. These aren't so small. Inside of them, we have a ton of libraries, and these actually use a ton of Amazon Web Services. Everything on pipelines is written in Java. It's battle-tested, well-documented, and it's easy to hire developers for. We use DropWizard to build RESTful services. DropWizard is just a bundling of Jetty, Jackson, and JaxRS. You can then add DropWizard as a dependency if you're using Maven and Gradle, and implement a few interfaces, and have a production-ready service up and running in minutes. We then use Hystrix, which is a library spawned out of Netflix for fault tolerancy. Whenever we want to make more requests, either to Bitbucket or to other microservices in pipelines, we wrap these in a Hystrix command. What Hystrix will then do is if the downstream service takes longer to respond, we'll sever the connection, and then we can choose whether to queue them up to let the downstream service recover, so we prevent DDoS attacks, and we can also return errors to users faster. And we've recently started experimenting with RxJava. This is another library spawned out of Netflix. It allows you to build asynchronous, reactive, non-blocking applications. Each of our services then runs on a single has an EC2 instance each, and we hide those behind load balancers, pretty typical for a modern web application. We store all of our data in DynamoDB. This is a NoSQL database provided by Amazon. And we use Elasticache for caching data for responses or objects and share these between services. And the entire actual backend architecture of pipelines is event-driven. And we use SNS and SQS to wire up those events. So digging a little deeper, we can see that we used a lot of libraries. Some of the things we have to implement are HTTP endpoints so that we can respond to requests from, say, webhooks when a repo push event occurs, or for the initial iframe page load, or when it makes further requests over AJAX for iframe data. The other entry point into a service is events. Events occur whenever something important happens in pipelines, such as a pipeline being created, a step being completed, or a pipeline being completed. The service is then free to choose how to handle this. It sometimes makes further requests to downstream microservices in order to enrich that request or to check for settings, such as checking if the counter is enabled or has build minutes left. We then make requests to DynamoDB to store stuff, and if it was something of importance happened during this request, we'll fire off an event for further services to action. So you can see microservices, they aren't so small. And building these with battle-tested open source libraries, we can accelerate our time to market with our services. And by building on top of AWS, we don't have to worry about how infrastructure works. So how do we actually then set up AWS? We don't want to be logging into that Amazon Web Console all the time, just configuring servers. That will get quite boring. And it's tedious, and it's error-prone, as no one can review what was actually changed. So Amazon provides a technology called CloudFormation. With CloudFormation, you can specify in your YAML your entire service infrastructure. Here, we have one for typical microservice pipelines. It requires a DynamoDB table, a load balancer, and a couple of EC2 instances. The cool thing is I can then check this into my repository and treat my infrastructure as code. I can have developers and operations personnel review this to make sure that it is correct, and it's also versioned so I can roll back to previous infrastructure stacks. Then, to spin up all these resources in AWS, I can use AWS CLI and one simple command with CloudFormation create stack. I could even automate this as part of my pipeline so that I could use pipelines to spin up this stack that it's running on. So once you have a stack up and running, how do you deploy new versions of your service? Amazon provides another technology called code deploy for this. How this works is you usually produce a bundle as part of an artifact as part of your build. For code deploy, this has to be an application bundle. Here we have an example of one. It's just simply a tar.gz file. Inside of this bundle, we have a directory containing the jar for our microservice. We have an app spec YAML, and we have some scripts that will start up and shut down the service. What will happen is when the code deploy agent, which is running on EC2 instance, detects that there's a new version of this bundle available, it will download it onto the instance. It will then it will then run some lifecycle hooks, which code deploy has. Two of them are application stop and start. What it'll do is it'll stop the current running service on that instance, and then copy over the new service jar, and then start up the new service. And it'll do this in a way that you can have zero downtime deployments. What actually happens is the code deploy agent will coordinate between your EC2 instances and only upgrade one at a time. If any of them errors, it'll roll them back to a previously known healthy state, and then you can debug why you could not deploy. So once you've got your infrastructure up and running and you can deploy services, how do you make sure these are actually running in production? And you need some greater insights. So we use Datadog on pipelines to monitor our services in production. Datadog is a monitoring and alerting solution. What happens is we run a Datadog agent EC2 instance. This catches instance level metrics that we can then report on, such as, say, from Docker to get the number of running containers. And it also has a web crawler so that it can actually scrape data from non-instance level services in Amazon, such as DynamoDB. We then start creating dashboards for all this. Here's an example dashboard. All the widgets on the screen are user customizable, and you can choose multiple styles of them. And this updates in real time. So as new data comes in, these wallboards update automatically. So you can put these around your office, and you'll be able to have insight into the typical healthier service. The other awesome thing about Datadog is you can set up alerting. So if you look at the CPU utilization rate there, we could set an alert to say if it goes above 60%, fire off an email or a PagerDuty to notify a developer that something is going wrong. And Datadog will handle this for you. So you can see, by using battle-tested open source components, you can accelerate your time to market. By building your code on top of Amazon Web Services, you don't have to worry about infrastructure. And by using CloudFormation and code deploy, you can deploy your code quite quickly. And using Datadog, have real-time insight into the health of your services. So now we have seen how using Connect, you can provide seamless integrations, and also with Atlassian cloud products, and what a typical microservice looks like in pipelines. Let's have a look at how we use Docker. We use it both locally for our development environments, and we also use it in the cloud to run builds for pipelines. So what is Docker? Docker is a lightweight virtualization software that uses hooks in the Linux kernel to allow you to sandbox compute, memory, and file system resources so that services look like they're running in their own OS, and they can't attack it. If any have security vulnerabilities, they can't affect other services running on the same instance. So here we have a typical development machine which has Docker on it and a working directory containing some code that I like to compile. Usually I'd have to download a JDK, configure it, and make sure that it works. And if I had multiple instances of the JDK, I'd have to be constantly changing environment variables to be able to use it, which is quite cumbersome. But what Docker allows you to do is spin up a JDK inside of Docker to compile your code. Here we have a Docker run command. Let's walk through this example a bit. The first argument to Docker run with -v is the volume. Here I'm saying I would like to mount my current code, which is on my machine, into the container. I then have the next argument, -w, short for working directory, specifies the directory that the commands will be executed in inside of the container. I've then given it the container. I've then specified which container I'd like to use, which is the OpenJDK with the 8th version of the JDK. I can then add my Java commands onto the end. What Docker will then do is download this container, which has Java inside of it. It'll mount my code into it, and it'll run the commands that I've attached to the end and compile my code. The cool thing is I haven't even got Java installed on my machine. It sits inside the Docker container, and then the container goes away once it's complete. The other nice thing about this is if I wanted to compile this, say, against version 9 of the JDK, I can just simply change a tag. So if you can see the image there now, it has a new tag. So after you compile your code, you probably want to start interacting with some services, such as a database like Postgres. Usually I'd have to download and install this and make sure it was secure. Otherwise, I could have security I would have security vulnerabilities on my developer machine. So with Docker, once again, I can specify another run command. Let's walk through the arguments on this. I've got a flag that says -d, short for detach. Docker will run this container in the background and make sure that it keeps it alive. You should use for long-running processes, such as, say, a database. And I've given it a name with Postgres here, so I can easily refer to it. And once again, I have to provide the image and the version number that I'd like to use. Once I run this command, I then have a running instance of Postgres on my machine. The nice thing is now this is isolated from all the other processes running on the instance. So if Postgres goes down, if I want to stop Postgres, I can just simply destroy the container and no longer have it running. Also, I can then link my containers together with this link argument. What this will do is it'll pull my image again, which has Java in it, and set up a two-way and mount my code, and it'll set up a two-way communication layer between my Java container, running my Java commands on my service, and in Postgres. So now I can consume services inside of containers as well. But you can see those commands are quite cumbersome. You can't share them with other developers, and they're very hard to remember. But what you can do is you can treat your local environment as code. Docker provides a technology called Compose. With Compose, and in a small YAML file, you can specify all the settings that we just were specifying at the command line before. Here, I've said I would like two service containers, one running Java and one running Postgres. Then the arguments that I specify become settings under these. And then now I can also spin up both of these services and have them running with one command, Docker Compose up. The cool thing is it'll manage pulling the containers and linking them all together. And I can check this into my repository. The nice thing about this is that other developers can now start with the same environment that I had. And I can version this with specific versions of what I'm committing. If I then want to pull down all those containers and no longer have them running, I can use one command once again. So we can see with Compose, we can share our development environments between multiple developers. But what happens if you want to containerize your own services and not just consume others? Docker has a technology called Docker files to control this. In the Docker file here, we're simply specifying that we'd like to containerize our application. I've specified a base image using the from argument. I will then build upon the OpenJDK image and add my own service to it. I then have a second argument that will then take my service jar and copy it into the container. And I've given it an entry point, so when a user runs this container, it'll start running my service. Then I can just modify the compose file that I had before to have an extra container, this time actual service. From this, I've also had to specify some build settings. I have a context which says use the current directory, which should have my service jar in it. I can then, using Docker Compose build my container. Now I can start consuming my own services and containers and make sure that all my services are isolated. So if there's any vulnerabilities or bugs in a service, they should not affect other ones. The cool thing is once I'm ready to deploy this or deploy this to other users or developers for other people to consume, I can just re-tag it, this time with a different tag for production, and push it up to Docker Hub so that other users can start consuming this service. So you've seen how we can use Docker to speed up our local development environment, and we can now share developer settings between people using Docker Compose files. But how do we run these containers in the cloud, especially when we want clusters consisting of thousands of running containers? We use Kubernetes in this in pipelines. So the smallest schedulable unit in Docker is a container. For Kubernetes, and you've probably realized that a lot of these containers are highly related, such as the Postgres and Java example from before. So let's walk through a different example. This time, we have a container that contains a web server, maybe Nginx, that serves up static content. I then have another container, such as a file synchronizer, that is constantly maybe pulling from a repository new files to be served. And I don't want to run these on different instances in my cloud. Otherwise, they'd have to communicate over HTTP, and it could be quite latency intolerant. What I can do with Kubernetes, however, is wrap these two containers in a pod. A pod now is scheduled on one instance. And the cool thing about this is it gives them a shared network and a shared working directory. With the shared network, all the containers can communicate with each other over localhost, which is quite nice, because now you can think of pods as an actual machine that can move around your cloud at will and go up and down. Kubernetes also does its best to keep these pods alive. So if this pod was to crash or to become in an unhealthy state, such as say if the web server went down, Kubernetes will kill that pod and spin up a new one. It works via a resolve review loop that it constantly does. It looks at the current state of our cluster, sees what the correct state should be, and it tries to get there. This might consist of rescheduling pods or spinning up and down new nodes as required to be able to schedule those pods. So once you have multiple pods in the cluster, how do you expose those to each other so that users can start talking to Kubernetes as well? So Kubernetes has this concept of namespaces. Namespaces allow you to group pods together. Here we have 2 instances with 4 pods running. I have pods in namespace A and pods in namespace B. The cool thing that I can do now is generate tokens so that these pods could talk to the Kubernetes over REST. And the tokens will be associated with a namespace. That way, I can use the Kubernetes REST API in a multi-tenanted nature. And much the same as Docker, Kubernetes can be completely controlled using a simple CLI tool, kube control. With kube control, I can use it to create namespaces, pods, delete them, and interact with my entire cluster. So now that you've seen, I've given you a small taste of Kubernetes. I could easily spend a whole hour talking about that. And we've only just started experimenting with some of the new concepts of Kubernetes, such as network-level isolation in namespaces. So obviously, we run thousands of containers in the cloud. And they're running in a multi-tenant environment, so we can be running multiple builds on a single EC2 instance. How can I make sure that my containers, whilst they are still isolated, are secure to prevent customers' builds from leaking to each other? Here, we have a typical node that runs in our cluster, and it has Docker on it. Maybe we want to expose Docker to the container so that it can perform, say, build commands. This was originally done using a privilege mode argument to a container. What Docker would then do is mount specific host directories from the Linux from your host into the container. Now, if there's ever a security vulnerability, either with your application or with the container, you might be able to then have a malicious user privilege escalate and start attacking the host, and then start destroying other containers that are running on it, such as other customers' builds. However, there is a nicer alternative to this. If all you want to do is expose Docker to containers, you can just simply mount the Docker socket into the container and install the CLI into that container. The nice thing now is that you're interacting with Docker on the host, and you can spin up containers that live on the same host next to you that you're now in full control of. These can come up and down at will. The cool thing with sibling containers is that you can now customize the arguments that you run. And this is similar to how the pipelines build agent actually does the builds. It spins up one sibling container to do the Git clone, and then a subsequent one to run, which is specified in your YAML, your custom image from your YAML, and runs your custom build scripts. So you've seen how with sibling containers, you can expose Docker to your services and still be secure. But let's talk about user namespaces. So here we have another instance, another node in our cluster that is running multiple containers, maybe say builds inside of them. And each of these containers has a different user inside of it. One is running as root, and one is running as build user. However, containers running on the host are actually running as root. This can be an issue because if there's ever a bug in Docker or a vulnerability in a specific version of the Linux kernel, and they manage to run commands in host space, they'd be able to do some real damage because they're root. However, by adding one simple argument to your Docker daemon on startup using user ns remap, what Docker will do is create a new user and group on your host called doc remap. Now, all containers are started as this user on the host. So even if there was a bug in the Linux kernel or inside of the Docker CLI, privilege escalation attacks would now be quite minimal, as they couldn't do much as this user. So we've seen how Docker provides strong compute, memory, and file system isolation. Let's talk a bit about networking, as this one's a little trickier. Here we have another node with some containers running, and these containers are talking to the outside network. What happens with Docker, it sets up a bridge adapter that allows the Docker containers to talk to the outside internet. This bridge, however, this bridge, and all packets travel over this. All the containers are attached to this single bridge. And if we spin up another container, we could actually start sniffing for packets on this bridge, as every single packet going out to the outside internet is now running on this. This could be quite bad, because another container in, say, our build cluster might be able to intercept sensitive data that your build is producing. Luckily, Docker has a way to disable this. You can turn on IP tables and disable inter-container communication, once again with the daemon. What will happen then is every time you spin up a new container, Docker will create an IP table rule for it. IP tables are simply rules that specify what packets should do when they're being routed to a container. The Linux kernel will then choose whether to allow these packets into this sandbox or drop them. By default, it sets up to drop all the packets except those specifically designated for that container. So now you can only sniff for packets that were destined for you and no longer from other customer builds. But this then stops containers from being able to talk to each other, unless they're explicitly linked. So now when you link containers, like we did before with Java and Postgres, Docker will set up dual rules in the IP table. This will allow the containers to talk to each other over the network again, and it will set up rules such that only those two containers can send network traffic to each other. So we've seen how you can use Docker in the cloud in quite a secure manner. You should be using user namespace remapping to prevent vulnerabilities in Linux kernel or in the Docker CLI from affecting you, and how to expose Docker in a secure way using and how to expose Docker in a secure way using sibling containers. So we're getting towards the end of my talk. We've seen that with Connect, you get a transparent entry point to all of Atlassian's cloud products. With microservices and AWS, you can accelerate your development by not having to focus too much on where it is running and can focus on your integration's business logic. And with Docker, you can see how you can use it to speed up your own development, how to easily share development environments, and how to run it at scale in a secure manner. Over the last half hour, we have covered how the pipelines team uses Connect, microservices in AWS, and Docker to provide a seamless continuous integration solution feature to Bitbucket Cloud. From these learnings, I want you to go back to your own companies and start using the same tools to produce amazing integrations. I look forward to seeing and using what you all create.
Okay, we got a few questions from the room.
Yeah, sure.
Did you explore Docker Swarm?
Yes, so we originally were running on ECS for our builds, and it's, how can I say this in a nice way? It's very hard to monitor containers running on ECS. Is the moment that so our builds are ephemeral, so they come up and down as required. Every time a build would finish, ECS would delete all the logs and associated metrics for it, and we couldn't actually debug what was happening. We then looked at Docker Swarm as a solution, but this was back before they had the application bundles. And Swarm is still quite limited in functionality compared to Kubernetes. So Kubernetes does more than what Swarm can actually do currently. Yeah.
Okay. Our application requires a large and complex database that has a small schema changes between versions. How can we effectively implement this?
Small schema changes between versions.
That might be a little deep.
Yeah, maybe you find me after the talk so I can talk that one through.
Okay. I've seen in pipelines, pipeline adds build status icons to various places, for example, merge dialog.
Yes.
Are these single icons also iframe?
No, so those ones are actually part of core Bitbucket. So Pipelines itself is an integration, so it's actually built by a completely different team to Bitbucket Core. So Bitbucket Core is based here in San Francisco, and Bitbucket Cloud is written in Python. With Pipelines, we're in Sydney, and all of our services are running on AWS, and they're in Java. So all the UI points, the only UI points we inject into Bitbucket Cloud are the build results. The build result that when you click through to a build from the dialog from those build status icons, the variables endpoints, and the pipeline overview page in the left-hand side panel. So those ones are actually part of core Bitbucket.
Okay. When will Bitbucket Pipelines be available for Bitbucket Data Center?
So the official solution for behind the firewall still is Bamboo. So Pipelines was built mainly for the cloud, and it was to serve a different niche of the market. So we wanted to accelerate people being able to jump into CI/CD by providing a simple build tool for now. We plan to expand the functionality of Pipelines in the future, but there's no plans to move it back behind the firewall. That's still Bamboo's space, and it's killing it there. So Bamboo's better for server.
Okay. How is production upgrade strategy?
So are we talking about Kubernetes or our services? Because we have two different strategies for that. So with our services, we basically deploy those as containers as well. So each container is promoted through our environment. And the way we do that is we have an internal platform called Micros at Atlassian, and it manages setting up the CloudFormation scripts for us. And the upgrade strategy is that on each instance, it'll spin up the new service, do some health checks that we can specify some endpoints to make sure that it works. And unless that was successful, it'll kill the new one and redeploy it'll like bring up the new container, the old container that was running the old version of the service. And that's how we do like live upgrades. With Kubernetes, we actually have the masters behind a load balancer, and we have 3 masters running at any given time. When we take down one of those for an upgrade, the other 2 masters can still satisfy requests, and then we do that like in a red-blue deployment where we do like 1, 2, 1, 2.
Okay, that's the questions in the mobile app. Do we have any live questions here in the room? Put your hand up if you'd like to ask any more questions. Going once, going twice. Okay, great. Hope to see you at Ship It Live. Thank you, Nathan.
Cool.